Hello students, how are you all? Hope you all are doing great and following my YouTube channel and seeing my video lectures and preparing the units of chemistry class 12. So let us proceed children with another important and very interesting and easy unit of class 12 organic chemistry, that is amines and diazonium salts. Some important compounds containing nitrogen. That will include amines and diazonium salts. So let me give you the general introduction of amines. Amines are the alkyl or aryl derivatives of ammonia, and they are formed by the replacement of maybe 1, 2 or 3 hydrogens attached to the nitrogen of ammonia by either alkyl or aryl group. So amines are said to be the alkyl or aryl derivatives of ammonia. So let us take ammonia here, and if we replace one of the hydrogen of ammonia attached to nitrogen by one alkyl group, let's say methyl group, we get a 1 degree amine. If we replace yet another hydrogen then by alkyl group, then we get a 2 degree amine, and followed by the third hydrogen attached to nitrogen. If further replaced, then we get a 3 degree amine. There is a lone pair of nitrogen which may form a coordinate bond with yet another alkyl group, resulting in the formation of another category called quaternary ammonium salts. So this was the general introduction of the amines, and now let us look at the structure of amines. Now children, you have studied the structure of ammonia in class 11 chapter chemical bonding. So here, if you just correlate the structure of ammonia with amines, you will find that there is similarity in the structures of both. In amines also, whether it is 1 degree, 2 degree or 3 degree, the nitrogen, the central nitrogen atom is sp3 hybridized. If it is in sp3 hybridized state, the geometry should have been, according to VSEPR theory, the geometry should have been tetrahedral. But here, just look that nitrogen is forming 3 bond pairs and 1 lone pair is left on the central nitrogen atom, giving rise to 2 types of repulsions, bond pair, lone pair, and bond pair repulsion. So its shape remains, or its geometry remains no longer tetrahedral, rather becomes distorted pyramidal shape. And its bond angle also does not remain the tetrahedral angle of 109 degree 28 minutes, but reduces and becomes less than 109 degree 28 minutes due to possible repulsions. So this is all about the structure of amines. Now let us see the nomenclature and let us see a few nomenclature problems. Remember that the general IUPAC names of amines are alkane amines. So if you just see this first structure, you will find, if you select the longest parent hydrocarbon chain, the chain is containing 3 carbons. And to carbon number 2, NH2 is attached. So we write it as propane 2 amine. Look at the second structure. This in trivial system is also called isopropyl amine. The second structure is allyl amine in trivial system. So this is carbon number 1, this is 2, this is 3. So it is pro-2E1 amine, and commonly called allyl amine. Look at the third structure. It is an example of a 2 degree or a secondary amine. So the name is N-methyl ethanamine, because the bigger alkyl group is considered as the PHC and the smaller one considered as a substituent on nitrogen atom. Look at the next structure. It is again a 2 degree amine. So it is N-methyl aniline. That means one of the hydrogen of aniline is replaced by methyl group, so it becomes a 2 degree amine called N-methyl aniline. Another structure, if you just see the trivial name, it is called orthotolidine. Please note orthotolidine. But in IUPAC system of nomenclature, we will call it as 2-methyl aniline. So these were a few IUPAC names. Let us see another structure, NH2CH2O6NH2. It is hexane 1,6 diamine. A monomer, we have already studied polymers children. This is one of the monomer of the polymer nylon 6,6. Another structure, the PHC is this. So it is cyclopen 3-ene-1 amine. Cyclopen 3-ene-1 amine. And the last structure, this is the phenyl group which is attached. So 2-phenyl propane 1 amine. So practice a few more nomenclature problems from your NCERT and other refreshers. And now let us proceed to the next important topic, which is general methods of preparation of amines. We can prepare amines by reduction of nitro compounds. So when nitro compounds are subjected to treatment with any reducing agent, maybe iron in HCl, tin in HCl, or lithium aluminium hydride, or hydrogen in presence of nickel or palladium, all of them are reducing agents, so any of them can be used. That will reduce the nitro group into the amino group. So by reduction of nitro compounds, we can prepare amino compounds. In the same manner, if you take aromatic, that means nitrobenzene over here, and you reduce it by using lithium aluminium hydride, you can convert it to aniline. Aniline is NH2 group directly attached to the carbon of the benzene ring. Next is the very important reaction which we have already studied in the previous chapter also, haloalkanes and haloarenes, by Hofmann's ammonolysis of alkyl halide. Now when you treat any alkyl halide with ammonia, then one of the HX will be lost and it will be forming RNH2, that is 1 degree amine. Remember, the reaction does not stop here. Further, it may react with excess of alkyl halide to form a 2 degree amine, further 3 degree amine, and finally quaternary ammonium salts. So question often comes of 1 mark relevant to this, and that is why Hofmann's ammonolysis reaction is not a suitable reaction to prepare pure amines. The answer or the reason is, since you get a mixture of 1 degree, 2 degree, 3 degree and quaternary ammonium salts, so it is difficult to separate all these amines by fractional distillation. So pure amines cannot be obtained by this reaction, remember. Next is by complete reduction of nitriles. Nitriles means cyanides. And we have already studied this in our video lecture 1.3 relating to the name reactions, and this is an important name reaction called Mendius reaction. So when cyanides are subjected to complete reduction using lithium aluminium hydride or sodium and ethanol can act as a reducing agent, it will form 1 degree amine. Next is, and this reaction is called Mendius reaction. Next is from amides. We can prepare by 2 different reactions. Number 1, by the process of reduction. When you treat any amide with reducing agent, let's say lithium aluminium hydride, you can convert the amide into 1 degree amine. Why 1 degree? Because amides are terminal functional groups. Next is very important name reaction which often comes in the exam, and that is Hofmann's bromamide reaction, also called Hofmann's degradation reaction. Why degradation? Because it will decrease the number of carbon atoms. For example, we have taken amide. When you treat it with bromine in the presence of KOH or NaOH, you get amine with 1 carbon less than the parent amide. So where that 1 carbon goes, it is lost in form of K2CO3. So byproducts are K2CO3, KBr and H2O, and this reaction is descent down reaction or degradation reaction. Why? Because it is forming amine with 1 carbon less than the parent amide. Very important reaction and often used in conversions as well. The last is again a very important reaction called Gabriel's thalamide reaction. We start from thalamide. Thalamide, look at the structure of thalamide. It is obtained by treatment of phthalic acid with ammonia. So when phthalic acid reacts with ammonia, we get a cyclic amide called thalamide. And when it is treated with KOH, it forms, this hydrogen is replaced by potassium. So it forms N-potassium thalamide. Further on treatment with alkyl halide, it will form N-alkyl thalamide, where the potassium is replaced by the alkyl group. And finally on hydrolysis using NaOH, it will convert into the sodium salt of phthalic acid along with 1 degree amines. Now 2 questions often comes in the board exam relevant to this topic, and that is why Gabriel's thalamide is exclusively a method or a reaction to prepare primary or 1 degree amines. Look at this structure of thalamide. You will find that nitrogen is having only one valency or one hydrogen attached to it, which can be replaced by the alkyl group. Remaining two are bonded to C double bond O groups, so we can only prepare primary or 1 degree amines by this method. Now another question which is very important, which comes, that why we can only prepare aliphatic amines by Gabriel's thalamide reaction. Why can't we prepare aromatic amines? Now for the preparation of aromatic amines, here what has to be taken is the aryl halide. And in aryl halide, there is a partial double bond character in the aryl halogen bond, making it strong and difficult to be broken. So these were the different methods to prepare amines, and now we will proceed with the next topic. Let's now study the physical properties of amines. The first physical property of amine is that in the actual state the amines are colorless, but when oxidized, as a result of oxidation, they will develop color. The second important property is the boiling point. And there is a 1 mark question in the board exam that arrange 1 degree, 2 degree, 3 degree amines in the order of their boiling points. So remember, 1 degree or primary amines have the highest boiling points as compared to 2 degree and 3 degree. So this is the order of boiling points of amines. The reason for this variation is that the extent of hydrogen bonding decreases as we move from 1 degree to 2 degree, as we move from 2 degree to 3 degree. So due to the greater or the maximum extent of hydrogen bond that primary or 1 degree amines form, they have the maximum values of the boiling points. Next is let us compare the boiling points of amines with alcohols. See, both amines and alcohols have ability to form intermolecular hydrogen bond, because the conditions for the formation of intermolecular H bond are presence of FON, highly electronegative element, along with free hydrogen. So alcohols also have oxygen, amines have nitrogen, and both of them have free hydrogen, so they can form intermolecular H bond. But remember that the hydrogen bonds formed by alcohols or carboxylic acids are more stronger as compared to those formed by amines, on account of high electronegativity of oxygen in comparison to nitrogen of amines. So the boiling points of amines are less than alcohol is again a very important 1 mark question that comes in your board exam. Next is solubility, and all those compounds which form intermolecular H bonds with water are readily soluble in water. Likewise, amines also form intermolecular hydrogen bonds with water, so they are also readily soluble. But remember that the solubility will decrease with the increase in molecular mass. And aniline or aromatic amines are insoluble in water. The reason being that the bulky aryl group in aniline offers steric hindrance in the formation of intermolecular hydrogen bond. Therefore, it is almost insoluble in water. Now, let us study the chemical properties, and the very first chemical properties of amine is basic character of amines. So, basic character of amines, let us see that nitrogen in amines bears a lone pair. So, because it is having a lone pair and it can donate its lone pair, hence it will act as Lewis base. So, with water it will form RNH3 plus OH minus, and if you write the Kb, that is dissociation constant of base expression, it will be Kb equals to RNH3 plus into concentration of OH minus divided by the concentration of RNH2, that is amines. And remember that Kb is the measure of basic strength of any amine, and it is inversely proportional to pKb, because pKb is the negative log of Kb. So pKb is negative log of Kb, that means pKb and Kb both are inversely proportional. That means stronger the amine, Kb will be higher but pKb will be lower. Now let us compare, this is a very important topic, alkane amine, the basic nature or basic strength of alkane amine versus ammonia. Now if you see that both are having nitrogen, and in both the cases nitrogen is bearing a lone pair. In aliphatic amines, the R group tends to exert the positive inductive effect. That means the plus I effect or the electron releasing effect releases the electrons and makes the availability of lone pair on nitrogen much more in aliphatic amines as compared to that in ammonia. Therefore, aliphatic amines are stronger bases than ammonia. Now let us see, this is also a very important concept here, which is often asked in 1 mark question in the board exam. Order of basic strength. Order of basic strength, if you see, in gas phase, 3 degree amines you find to be most basic as compared to 2 degree and 1 degree. And this order can be explained on account of the inductive effect. Since in 3 degree amines there are 3 R groups and all of them are exerting the positive inductive effect plus I effect and increasing the availability of the lone pair on nitrogen to a maximum extent, which makes 3 degree amines most basic in nature. But this was in gas phase. But if you see in aqueous phase, then the basic strength of amines in aqueous phase is not only governed by one factor, inductive effect, but 2 other factors also play their important role. The second factor in addition to the inductive effect is steric factor, and the third factor is the solvation effect. Since it is an aqueous phase, the amines get solvated. Solvated means they get surrounded by the solvent or the water molecules and release a large amount of solvation energy. So here the order in aqueous phase, if we talk of ethyl and higher amines, the order, remember, is 2 degree more basic than 3 degree than 1 degree. But exclusively for methylamines, where steric hindrance, steric factor does not play its major role, since the methyl group is a very small group. So the order slightly changes and it becomes 2 degree more basic than 1 degree than 3 degree. So these 2 orders are very, very important in aqueous phase. And you have, and if it is asked to arrange the given set of amines in the order of their basic strength, and if nothing is mentioned, then by default you have to consider in aqueous phase, where you have to remember the order 2, 3, 1, 2 degree more basic than 3 degree than 1 degree for ethyl and higher amines, and 2, 1, 3, 2 degree more basic than 1 degree than 3 degree for exclusively methylamines in aqueous phase. In gas phase, the order is 3 degree more basic than 2 degree than 1 degree. So this was all about the basic character. This is a very, very important topic of amines. Now we come to the comparison of the basic strength of aliphatic amines versus aromatic amines. For example, if a question comes for 1 mark in board exam, that out of ethanamine and aniline, which is more basic and why? So obviously ethanamine is more basic. I'll tell you the 2 reasons for ethanamine being more basic in nature. In case of aniline, the lone pair on nitrogen is involved in the resonance with the benzene ring. Therefore, it is not readily available for donation. But in case of aliphatic amines, the R group, the alkyl group, tends to exert the positive inductive effect and increases the availability of lone pair on nitrogen, making aliphatic amines more basic in comparison to the aromatic amines or maybe aniline. Now let us see what is the effect of substituents on the basic strength of amines. See, substituents which are attached to the benzene ring, they are of 2 different types, that is electron withdrawing groups and electron donating groups. Electron donating groups tend to exert the plus M or positive mesomeric effect. A few examples are CH3, OCH3, NH2, OH. All these are electron donating groups. But electron withdrawing groups, they tend to exert minus M or minus R effect. And the examples are CN, NO2, CHO and COOH. So remember that the electron donating groups will increase the basic strength of amines. That means they will increase the Kb and decrease the pKb. Whereas the electron withdrawing groups will decrease the basic strength of amines. They will decrease the Kb and increase the pKb. So this is very important concept. Effect of substituents on basic strength of amines. Now we come to chemical properties of amines, and let us study the chemical properties, the very first property, which is alkylation. Alkylation here refers to the replacement of hydrogen attached to the nitrogen of amines by alkyl group. So here, when you treat it with alkyl halide, then 1 degree amine converts to 2 degree. Further on treatment, it converts to 3 degree, and further it forms quaternary ammonium salt. So when we take here, suppose R is CH3, or we take methyl halide, then this reaction is also called exhaustive methylation. Next is acetylation. We have two acetylating agents, CH3COCl or acetic anhydride. So when you treat amines with any of the acetylating agent in presence of base, then it will form substituted amide. What happens is the active hydrogen of the amines get replaced by the acetyl group. So it will result in the formation of substituted amide, no matter whether you use CH3COCl acetyl chloride as the acetylating agent or acetic anhydride as the acetylating agent. For example, if we take the aromatic amine aniline and react it with CH3COCl in presence of base, then it forms a substituted amide again, and the common name of this is acetylide. So when we will discuss about aniline, we will discuss a very important question, that why do we need to protect the amino group of aniline by acetylation? So here we will discuss the answer to that question, this question in the next topic. Reaction with chloroform and KOH. This we have already discussed in the name reaction video lecture. This is called carbylamine reaction. It is the characteristic reaction of 1 degree amines and may be used as a test of distinction to distinguish between 1 degree versus 2 degree amines or 1 degree versus 3 degree amines. So when you treat any 1 degree amine made to be aliphatic or aromatic with chloroform and alcoholic KOH, we get the offensive smelling or foul smelling carbylamines or isocyanide along with KCl and water. And therefore this reaction is also called isocyanide reaction or carbylamine reaction. The last reaction here is the reaction with nitrous acid HNO2. 1 degree amines with nitrous acid will form alcohols. This we discussed in the chapter alcohols, phenols and ethers. And 2 degree amines with nitrous acid will eliminate water and form yellow oily liquids called N-nitrosamine. And 3 degree amines will react with nitrous acid to form quaternary ammonium salt, trialkyl ammonium nitride. So these are all the chemical properties of amines. Now we will study about the aniline. Let us see now the chemical properties of aromatic amine aniline in form of a flowchart for easy memorization. So the very first property is treatment with aqueous bromine. With aqueous bromine, the NH2 group being highly activated activates the 2 ortho and 1 para position simultaneously, resulting in the formation of a tri-bromoamine derivative of aniline. So what is formed in the reaction is 2,4,6-tri-bromoaniline. But if we want a mono-substituted bromo derivative, for that we need to protect the amino group by acetylation. Acetylation will reduce the activating power of the NH2 group attached to the benzene ring in aniline, and it will result in the formation of acetanilide. In acetanilide, the C double bond O group is in conjugation with NH group, and hence the lone pair of nitrogen is involved in resonance, due to which the activating power gets reduced. So we have, for forming the mono-bromo derivative, we need to subject aniline to acetylation by treatment with CH3COCl in the presence of pyridine, so that it forms acetanilide. Further, this acetanilide on reaction with bromine in the presence of acetic acid will form 2-bromoacetanilide. 2-bromoacetanilide then subjected to hydrolysis in acidic or basic medium will convert into 2-bromoaniline. So here we get we can get here ortho and para. We will get here ortho and para bromo products. So here I have shown only ortho, but in addition to that we will also get para bromoaniline. So if we want a monosubstituted derivative, we need to first react with aniline with CH3COCl, that is subjected to acetylation, followed by treatment with bromine in presence of acetic acid. Next reaction is nitration, and nitration is done using nitrating mixture, which is a mixture of concentrated HNO3 and concentrated H2SO4. At 288 Kelvin, since here we know that NH2 group is ortho-para directing. But if you look at this reaction nitration, you are getting not only the ortho and para product in 2 and 51% yield respectively. Along with that, substantial amount of, that is 47% yield of meta-nitroaniline is also obtained. Despite of the fact we know that NH2 group is ortho-para directing. See, this question often comes in one mark in the board exam. And why are we getting the meta derivative in addition to the ortho-para derivative as a result of nitration? The reason is that when aniline reacts with H2SO4, it forms an intermediate anilinium ion, and this anilinium ion is meta directing. So in addition to the ortho and para product, we get meta product also in a substantial yield, that is 47% yield as a result of nitration of aniline. The next is sulfonation. Sulfonation is done by treatment of aniline with sulfuric acid concentrated so that it forms a anilinium hydrogen sulfate, which further on rearrangement will form 4-aminobenzene sulfonic acid, commonly called sulfenilic acid. And since it is having both the groups, acidic as well as basic, there will be transfer of a proton from SO3H to NH2 so that it forms a Zwitter ion of sulfenilic acid. About Zwitter ions we will study in the chapter biomolecules, but for here remember they are dipolar ions which bear positive and negative charge within the same molecule. So sulfonation forms sulfenilic acid, that is 4-aminobenzene sulfonic acid, which can exist in form of its Zwitter ion. Next reaction we have already studied in the amines portion, that is the carbolamine reaction. So whether it is an aliphatic amine or aromatic amine like aniline, both of them can undergo carbolamine reaction. On treatment with chloroform and KOH, they will form foul-smelling carbolamines or isocyanide. So here phenyl isocyanide is the major product along with KCl and water as the byproduct. Next reaction also we have already studied that when aniline is treated with NaNO2 and HCl at a temperature of 0 to 5 degree, then the reaction is called diazotization reaction. It results in the formation of benzene diazonium chloride. Now, one more question often comes in the board exam, and the question is why aniline does not undergo Friedel-Crafts reaction. Aniline will not undergo Friedel-Crafts reaction because the aniline acts as a Lewis base, and in Friedel-Crafts reaction we use anhydrous AlCl3, which tends to act as a Lewis acid. Now both of them react to form a salt, and because of the salt formation there arises a positive charge on nitrogen which deactivates it, and hence it will not show Friedel-Crafts reaction. Remember, 1 mark question, very important question. Aniline does not undergo Friedel-Crafts reaction. The last topic of the chapter is diazonium salts. Now diazonium salts we have studied are prepared by diazotization reaction of aniline. Just see, aniline when treated with NaNO2 and HCl at 0 to 5 degree forms the benzene diazonium chloride, or benzene diazonium salts are formed. Aliphatic amines cannot form diazonium salts. The reason being the aliphatic diazonium salts are unstable on account of absence of resonance. Now let's see the flowchart of the chemical properties of the benzene diazonium chloride. Most of the reactions we have already studied earlier. For example, Sandmeyer reaction. Sandmeyer reaction involves the treatment of BDC with maybe copper chloride in presence of HCl, to form chlorobenzene, or copper bromide in presence of HBr to form bromobenzene. The similar reaction here is Gattermann, where instead of using copper salt of bromide and chloride, we use copper powder in the presence of HCl or HBr so as to give chloro or bromobenzene. So BDC can be converted to haloarenes like chloro and bromobenzene as a result of two reactions, that is Sandmeyer reaction or maybe Gattermann reaction. The only difference between the two is in their reagents. In Sandmeyer we use CuCl in presence of HCl or CuBr in presence of HBr to produce chloro and bromobenzene. But in Gattermann we use copper powder in presence of HCl or HBr. Next is the reaction of BDC with CuCl in presence of HCl to form cyanobenzene. Next is if you warm BDC with Ki. On warming with Ki you get iodobenzene along with the byproduct KCl and nitrogen. The next reaction also has been studied earlier, and that is reaction with fluoroboric acid followed by heating. So an intermediate benzene diazonium fluoroborate is formed which dissociates to form fluorobenzene BF3N2 and HCl. This is a very important name reaction called Bals-Schiemann reaction. Treatment of BDC with HBF4 followed by heat to form fluorobenzene as the major product is Bals-Schiemann reaction. A similar reaction which is comparable to this is HBF4, NaNO2, copper and heat. In the presence of all these reagents and conditions, we can convert the BDC into nitrobenzene along with the byproduct NaBF4 and N2. So you have to remember that there is a confusion between these two reactions and you have to see the reagents before you write the final product. So when it is only HBF4 and heat, then fluorobenzene will be formed. But when HBF4 along with NaNO2, copper and heat are the reagents, then instead of fluorobenzene, nitrobenzene will be formed. This reaction next reaction has been studied in the chapter alcohols phenols. That when you treat BDC with warm water, you get phenol as the final product. Now, how can you convert BDC to benzene? Look at these two reagents and try to learn that BDC when treated with ethanol will convert to benzene. Ethanol will get oxidized to ethanol along with the byproduct N2 and HCl. In the same manner, when you treat BDC with H3PO2 in the presence of water, we get benzene along with H3PO3 oxidation product, N2 and HCl. So, benzene from BDC can be prepared, remember, by two reagents, either treatment of BDC with ethanol or H3PO2 in the presence of water. Next two reactions are comparable. They are called coupling reactions, which we have already studied in the name reaction video lecture 1.3. So coupling reaction involves the reaction of BDC with aniline to form a yellow color azodide. The name is 4-aminoazobenzene. It is a yellow colored azodide. And the last one is again the coupling reaction BDC treated with phenol. It will form 4-hydroxyazobenzene, again a orange color azodide. So both these reactions are called coupling reaction. BDC with aniline forms a yellow color dye, with phenol forms a orange color dye. So this is all about the chapter amines and diazonium salts. So just prepare this chapter thoroughly and solve the NCERT exercises given at the back. Thank you.